The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but
That's funny.
Isaac Asimov said that. And, it really captures the spirit of what we're diving into today. Sometimes the best solutions pop up when you hit a snag, something unexpected, and we definitely have a pressing problem right now. China's recent restrictions on exporting rare earth minerals and magnets, well, that's sending ripples everywhere.
Huge ripples.
Yeah, and it's not abstract. Look at Maruti Suzuki, India's biggest car maker. They've had to slash production targets for their Vitara EV by 2/3. That's a serious wake-up call.
It really is. And it's crucial to see this isn't just, one company's problem. It shines a light on a much bigger issue, this global dependence we have, especially for critical tech like EVs.
Right.
It basically screams for urgent strategic thinking. We need alternatives, reliable ones.
Exactly. So that's our mission for this deep dive. We're drawing on some critical discussions, including analysis published recently in Business Line, to explore two main paths India and really the world can take.
Two paths to less dependence.
Precisely. First, using magnets that, don't need rare earths at all. And second, maybe even more radical, motors that don't need any magnets, period.
Fascinating stuff.
Our goal here is to understand how these alternatives work, if they can maintain efficiency, maybe even improve it, and really pave the way for more self-reliance. This dive should give you a real shortcut to understanding a topic shaping mobility's future, right here in India. Useful stuff, especially if you're tracking current affairs, maybe for competitive exams like UPSC mains or prelims. These kinds of developments are key.
And if you look at the bigger picture, the strategic dilemma is, it's pretty stark, isn't it? China's dominance in rare earths is just massive.
Undeniable.
So any restriction they impose, it hits global industries hard, especially automotive, with EVs being so reliant. This isn't just about finding a new supplier. It's about nations needing technological sovereignty, building resilient domestic capabilities.
Okay, so with those stakes clear, let's get into India's response, starting with that first approach. Rare earth-free magnets. There's a company, Viridian Ingni Propulsion.
Right, Sriram Gopal's company.
Yes, their CEO, Sriram Gopal. They're developing a prototype motor using exactly that magnets without rare earths, specifically ferrite magnets in these permanent magnet-assisted synchronous reluctance motors. Sounds complex.
It does sound like a mouthful, but the core idea behind ferrite magnets is actually their sort of simplicity and availability. They are permanent magnets, but made from common stuff like iron oxide, other metallic oxides, not those tricky rare earths.
So readily available materials.
Exactly. And while ferrites aren't new, Viridian is really pushing the envelope, figuring out how to make them work effectively for demanding EV applications.
Okay, but the key question is always performance, right? How do they actually stack up against the rare earth versions? I hear Viridian's had some success.
They have. Quite a bit, actually. They've managed to match the efficiency of rare earth motors, and for four-wheelers, maybe even edge slightly ahead. That's pretty impressive engineering.
Match the efficiency. Wow. Okay, what about weight? Is there a trade-off there?
Good question. For four-wheeler motors, which usually use liquid cooling, they're basically on par. Weight-wise, it's about the same.
Right.
But for two- and three-wheelers, things are a bit different. Those often use fan cooling, and the ferrite motors end up being about 15 to 20% heavier.
Heavier. Why the difference?
It comes down to the cooling design. The fan-cooled versions need more copper in the windings to dissipate heat effectively. Copper is great for heat transfer, but, it adds weight. So there's a slight penalty there for the smaller vehicles.
Right, a design trade-off.
Okay.
But cost. That's often the bottom line. How do Indian ferrite magnets compare price-wise to Chinese rare earth ones?
Now that's a major advantage. They're significantly cheaper, a really substantial cost saving.
Okay, cheaper, efficiency is matched. But wait, you mentioned ferrite magnets aren't as strong, magnetically speaking.
That's the key technical point, yes. Rare earth magnets, they pack a punch, around 1.4 Tesla magnetic field strength. Ferrite magnets, much lower, only about 0.4 Tesla.
So less than a third of the magnetic strength. How on earth do they achieve similar performance then? That seems like the magic trick here. What's Viridian's secret sauce?
It is the core innovation. Sriram Gopal explains that in their specific motor design, that permanent magnet-assisted synchronous reluctance motor, the magnet itself only provides maybe 30 to 40% of the torque.
Only 30–40%. Where does the rest come from?
From something called reluctance torque. It makes up the other, say, 70%. Now, reluctance, it's basically a material's natural resistance to having magnetic force flow through it. Think of it like magnetic force preferring the easiest path.
Like water flowing downhill.
Exactly like that. Viridian's motor is cleverly designed to harness this effect. The magnet gives it a push, but most of the rotational force comes from exploiting this natural tendency of magnetism to follow the path of least resistance within the motor structure.
Yeah.
A simple analogy. Think of a fridge magnet. It snaps into place, right? That's not just the pull, it's also finding the spot where reluctance is lowest, the easiest place for the magnetic field lines. Viridian amplifies that principle.
Okay, that makes sense. It's about the whole system design, not just raw magnet power. Very clever. And beyond performance and cost, there's another big plus point you mentioned, the environment.
A huge one. Schramm really emphasizes this, manufacturing just 1 kilogram of rare earth magnet. That can generate somewhere between 75 and 130 kilograms of carbon emissions. It's quite energy intensive and involves harsh chemical processes.
Wow, that's a lot.
It is. Now compare that to ferrite magnets. Producing 1 kilogram of ferrite, only about 13 kilograms of CO2. That's nearly 7 times lower. It's a massive difference for sustainability, especially scaling up EV production.
7 times lower CO2. That's a compelling argument on its own. So great performance, cost savings, much better for the environment. What are the hurdles? What challenges does Viridian face getting these motors widely adopted?
The main one SRAM points to is actually a software talent gap. It sounds a bit surprising, maybe.
Where?
For a motor.
Yeah. See, when you develop this kind of indigenous solution, you don't just build the motor hardware. You also have to create the sophisticated controller and the software that runs it, all from scratch. It needs to be perfectly tuned to this specific motor design.
Unlike the imports.
Right. Often when you buy rare earth magnets, especially from major suppliers, they might come almost like a package deal with compatible controllers. With this ferrite approach, it's a ground-up development, needing very specialized skills and motor control software skills that aren't perhaps as common in the talent pool right now.
So building that specific expertise pipeline is key to scaling up. But the underlying technology itself, it sounds very promising. Is there external validation for this approach? There is, actually. A paper from 2022 published in a journal called MDPI's Energies. It's a respected peer-reviewed journal, directly looked at this.
What does it find?
It basically confirmed that these permanent magnet-assisted synchronous reluctance motors have, and I'm quoting loosely here, excellent features for EV applications. They highlighted cost, torque density, efficiency, and specifically recommended them for passenger cars, buses, even heavy-duty trucks. So, yes, solid external backing for the concept.
Okay, that's really encouraging for the ferrite path. Now let's pivot to that second option, which sounds even more, well, fundamental. Motors without any magnets, going completely magnet-free. What does that look like?
This takes us into the realm of induction motors, but perhaps advanced versions of them. The potential here is for something truly 100% indigenous, completely bypassing the magnet supply chain issue.
How do they work without magnets?
Well, a major player, like the Japanese motor company Nidec, explains it pretty clearly. Induction motors work on electromagnetic induction. Essentially, you use changing magnetic fields in the stationary part, the stator, to induce an electric current in the rotating part, the rotor. That induced current creates its own magnetic field, which interacts with the stator's field to produce torque. No permanent magnets needed.
Okay, induction motors have been around a long time, though, haven't they? Why aren't they the standard in EVs already if they avoid the magnet issue? I recall seeing some skepticism, maybe from the U.S. Department of Energy.
You're right. They are a mature technology, and the DOE did express some reservations. They acknowledge induction motors are reliable, have good starting torque. Some early EVs even use them. But their main concerns were around power density, how much power you get for the size and weight and overall peak efficiency compared to modern permanent magnet motors. Their view was sort of, that the technology had likely hit its ceiling for improvement, making it less competitive for future high-performance EVs in terms of cost, weight, and size.
So the established view was maybe good, but not good enough for the next generation.
Pretty much. But then you have compelling counterarguments coming from innovators, like Dr. R. Ramarathnam, the chairman of Basil Energetics, based in Chennai.
And what's their take?
Dr. Ramarathnam basically challenges that reached its limit view. Basil Energetics has apparently demonstrated that their DC induction motors can be highly efficient, reducing power consumption in tools and appliances, and critically can be used in vehicles without losing efficiency compared to magnet-based motors.
So they believe they've cracked the efficiency and density problem. Do they have proof?
They seem to.
No.
They actually demonstrated their induction motor for electric two-wheelers in Japan. And the results were striking. It achieved the same efficiency as a standard rare earth magnet BLDC motor. That's a brushless DC motor. Very common and efficient.
Same efficiency.
Same efficiency. And importantly, it was comparable in size and weight, too. Dr. Ramarathnam is confident they can develop a similar prototype for four-wheelers as well.
That's quite a claim against the conventional wisdom. Are there other advantages to induction motors besides avoiding magnets?
Yes, a really significant one. Temperature tolerance. This is a big deal. Induction motors inherently work well across a wide range of temperatures. Permanent magnets, on the other hand, can start to degrade, lose their magnetic strength if the motor gets too hot, say above 150 or 180 degrees Celsius.
Which can definitely happen in demanding EV use, especially in hotter climates.
Exactly. So that inherent temperature resilience of induction motors is a major plus for long-term reliability and performance, particularly somewhere like India.
Okay, so when Basil says their motor is comparable, what are they measuring against? What benchmarks did they aim for?
Dr. Ramarathnam mentioned they focus squarely on two key metrics, power-to-weight ratio and overall efficiency. The goal was to ensure their induction motor matched a comparable permanent magnet motor on both counts. He stressed efficiency particularly because lower efficiency means you need more battery power for the same range, which is obviously not what you want in an EV.
Right, so how did they do it? If the technology was considered mature, what innovations did Basil bring to motor design to achieve this parity in efficiency and weight?
It really sounds like meticulous engineering and maybe looking at details others overlook. Dr. Ramarathnam explained it involves minimizing energy losses that typically happen in induction motors, losses in the stator, the rotor, or the windings.
How do you minimize those?
Through careful design of the stator and rotor slots, these are the grooves where the copper windings sit. Getting those dimensions just right is apparently crucial.
Okay.
They also experimented with the motor's operating frequency. He gave an example. Motors designed for US standards often run at 60 cycles per second, or hertz, and tend to be lighter than Indian standard of 50 hertz motors. By increasing the operating speed, maybe by 20%, you can actually reduce the motor's weight, making it competitive with rare earth magnet motors.
Interesting. So tweaking the frequency impacts the weight.
Yes, and they apparently use proprietary software to model and select the optimal slot dimensions. A level of design detail he suggested isn't always pursued. It's not just assembling parts, it's deep design work.
And anything else?
Yes, the lamination design. This is fundamental. Instead of using solid blocks of metal for the stator and rotor, they use very thin sheets or laminations of steel stacked together. This drastically cuts down on energy losses called eddy currents, helping maintain high efficiency. It's a known technique, but perfecting it for high performance is key.
Wow. So it's a combination of detailed slot design, frequency optimization, specialized software, and advanced lamination techniques.
Exactly. It shows there was still room for innovation in induction motor design if you really dig into the fundamentals.
What an incredible journey through these alternatives. We've looked at two really solid pathways India is exploring. First, rare earth-free magnets like the ferrite tech from Viridian Ingni Propulsion.
Showing real promise in efficiency and cost.
Right. And second, pushing the boundaries with completely magnet-free motors like Basil Energetics advanced induction motors.
Which tackles the temperature issue head-on, too.
Looking at the bigger picture, these homegrown developments feel like more than just clever engineering, don't they?
Oh, absolutely. Strategically, they're vital. This isn't just about finding substitutes. It's about building genuine self-reliance for India, reducing that vulnerability to global supply chain shocks, especially from dominant players.
It strengthens technological sovereignty.
Precisely. The innovation happening right here has huge implications for India's EV industry, its manufacturing sector, and its whole economic future. It's about moving from being reliant to potentially becoming a leader in these alternative technologies, maybe even an exporter.
What a fascinating deep dive. We've seen how Indian innovators are tackling a major global challenge with ingenuity. Viridian's ferrite magnets matching efficiency, slashing costs, drastically reducing the environmental footprint. That's compelling.
Really compelling.
And then Basil Energetics, showing that magnet-free induction motors can indeed perform on par, maybe even better in some conditions like high heat. This exploration hopefully gives you that shortcut to understanding a complex but crucial topic shaping our future. Knowing about these shifts is key for grasping current events, industry trends, and the drive for strategic autonomy, super relevant whether you're studying for exams like UPSC or just want to be informed about where technology and geopolitics intersect. If you found this discussion useful, do like, subscribe, and feel free to comment with any further queries.
And maybe leave you with this thought to chew on. We've seen how focused indigenous innovation can tackle a major material dependency like rare earths and even yield environmental benefits. So where else might this be possible? What other global supply chain vulnerabilities in other sectors could be transformed by similar dedication to fundamental research and design, not just here in India, but worldwide? Something to think about.